Okay, so first off, you're going to need to be in Google Classroom because the assignment that we're working on is in the stream here, labeled Properties of Compounds Lab. Okay, right now, what you will see is that there are two things in here. There will be more. Okay, like for example, right now I'm recording what I'm going to tell you here and the tips and pointers and things like that for putting the lab report together. Okay, that will end up in here as well, as will the video of the lab itself, the observations and things like that. That'll end up in there. So there'll be a few resources in this thing here. So this will end up having about 4 layers, okay, by kind of the end of the day tomorrow. So this first sheet here, the PDF, is actually the actual lab sheet. It has all the instructions and wording and everything on it. Okay, and it looks like this. Okay, so it has everything on it. What else is in there is your copy of everything. So if you click on open, right, you'll see this come up. There'll be those two things there still, but there's also this now, and it'll have your name. Okay, instead of student code error, it'll say your name, properties of compounds lab report. Click on that and it'll open up the template for you to fill in. This is the document that you're filling in and handing in to me. Okay, so this is the way I want it brought in. I don't want it opened up in another program or something like that. Obviously, exceptions may have to be made, but okay. For everybody else, okay, it's going to be, you do it in the Google Doc that I've given you. Okay, submit it through Google Classroom. This document. All right, now, like I said, it's already set up for you, so it's saving you some work. Okay, what you're going to have to fill in basically is all the stuff that's blank, and that's what we're going to talk about a lot of today. I'm going to go through, because this is your first lab report, you're going to go through the expectations again for the variables and hypothesis this time in particular. We went over in general what the expectations were on Friday. So if you missed Friday's class, make sure you watch the video, which is part of this thing, on the expectations for a proper lab report. Okay, but we will go over today. Okay, some stuff in here. I'm going to lay it out for you pretty thick. Okay, in terms of I'm pretty much giving a lot of it away. So what you should be doing while I'm doing the explanation up here is you should be typing in some stuff in here. Not necessarily finishing it all, but as I'm talking, typing in a few hints or something, like, oh, Mr. Coder said this was something that needed to be in here, and he said this was something that had to be in this part, and that way when you come back, oh, right, I've got to do this or that for each section. Okay, and that's the way it'll work on every lab. I'll give you some tips and hints for each part, okay? And the expectation is that obviously you take those to heart, okay? The other part of it is I am recording all of this. So if you missed any of those tips and hints, you can always watch this again, and I highly suggest you do while you're putting your final lab report together. Be listening to this in the background and make sure that you're catching all those little tips and hints that I give out, okay? Expectations fairly clear there? All right. So the first thing that we have to look at is the problem, because in your version of this, it says you need to restate the problem in your own words, and that should also say in the form of a question, right? The problem should always be a question. So what we're looking at here for the problem is that we're going to be given several unknown samples. We talked about that on Friday. How can we classify them as ionic, molecular, acids, and bases in order to find their true identity? All right, so somehow you've got to put into your own words the problem about trying to find the identities of these unknown compounds. The next thing that you have to do, and we talked about this on Friday as well, is identify all of our variables. Right, so our manipulated variable and explain, our responding variable and explain, and 3 controlled variables with explanations of each one. What needs to be in the explanation? Well, for the manipulated variable, how are we manipulating it, and what effect do we hope it's going to have? Okay, so for the manipulated variable, okay, we want to include how is it being manipulated, okay, and what effect will that have? Okay, that's what should be in the explanation for your manipulated variable, and I'm going to go over that even more specifically here in a minute. Okay, for the responding variable, okay, what are we looking for? What's going to respond to what we did? How is it going to change? Okay. Okay, and of course, why? Okay, so why is it the responding variable? How is it going to change? And then, like we said, Okay, for the controlled variables, we want 3 of those. 3 controlled variables. Okay. How are they being controlled? Okay, what effect would they have? Effect, affect, yeah, whatever. Okay, question? We're going to talk about that. Okay, it is, yes, it is the outcome of what we do. Okay. All right. So we talked about this lab on Friday, and we said we're going to have a bunch of unknowns, 12 of them, okay, laid out in front of us, and we have to identify which one is which from a list of possibilities. The list of possibilities, incidentally, is here in your materials list. All right, well, we'll talk about that in a minute. So what did we say? What kind of test were we going to run? Anybody remember?
See what color we did.
Okay, so one of the things we were going to look for was color. What else?
Maybe the temperature.
Okay, we'll probably take the temperature as part of another test, but it'll be part of it. Odor, solubility, okay, conductivity of the solution, pH, those are all things that we were going to look at. But we were going to test every single substance the same way, agreed? Every single substance is going to get the same tests. Okay. So every time I run the tests, what am I changing? What's that? Okay, and what is the manipulated variable? That's what I'm, sorry, leading to here. Each time I run the tests, what changes? Exactly, the substance that I'm testing. So there you go, I just gave it away for you. Okay, the manipulated variable is the various unknown samples. Each time we run the tests, we're running it on a different sample. That's what we're manipulating as the experimenter. Now we're hoping, as a result of doing these tests on a different material every time, that we're probably going to get different data. At least that's what we hope. Okay. So every time I run the tests, I run it on something different. What's going to change then each time I run the tests on a different material? Okay, so what's the responding variable then? What am I looking for? Right, the results of each test. Hopefully they're going to be different. If they're not, we're going to have a really hard time identifying the unknown materials. Okay, if every single thing we test has exactly the same results, then we either had 12 samples that were identical or we're way off on how we think matter works. And we're not way off on how we think matter works. Okay, so we should hopefully have different results each time we test a new material. Okay. Now we said we need 3 controlled variables. In this lab, what are some things I want to make sure are the same every time I test a new material?
The thermometer.
Okay, so I could use the same instruments. That could be one. Yeah. How much is probably a big deal. Okay. I want to test about the same amount if I want my tests to be fair. Okay. I mean, how am I going to compare solubility if in one depression I put like a pile that's higher than the top, and in the other one I put 2 tiny little grains? That's hardly a fair comparison. So certainly, yeah, we should try and use about the same amount of everything. Okay, that way our tests are at least somewhat fair, right? And you can see the amounts are not going to be very big. This is the depression plate that you're going to be using tomorrow, right? We're not going to use very much. Okay. Okay, so amount, that's definitely a good one. What else? Has to do with the thermometer. What does the thermometer measure? Yeah. Okay. I mean, think about it, guys. If I'm testing solubility, is solubility affected by temperature? Right? If something's hotter, it usually dissolves better. So I probably want them all to be around the same temperature. Right? Is that something I'm actively controlling or passively controlling? Yeah, I'm passively controlling that. All of the materials for this lab I made up last week, and they've been sitting in the lab, which is 22 degrees Celsius, for almost a week. Okay, so when we use them all tomorrow, they'll all be 22 degrees Celsius. All the water will be 22 degrees Celsius. It's all the same. Okay, so we've got that part of the experiment controlled. Okay, because we don't want it to affect some of our tests. Some of our tests could be affected by temperature. Right? I'm really laying this out there for you guys. I don't see not everybody's typing what I'm saying here, but I've essentially given you 2 out of the 3 with explanations. Right? So it'd be a good idea to listen to this later, right? If you didn't type anything. Okay, third controlled variable. So we said amount and temperature. I need one more thing, and you guys are going to come up with this. Okay, one more thing that should be the same every time I test a new material. Okay. I'm thinking it's something kind of obvious and big. All right. Well, I'm not. Well, you guys are going to come up with the third one. All right. Okay. Questions on the variables? Okay. So the next part is the hypothesis. Now, what 3 words does the hypothesis have to have? If, and then. It's in your template. Okay. We talked about this on Friday, but here's how it works. The if part of the hypothesis needs to deal with the premise or the idea that we are working on or trying to prove. Okay? The and part briefly describes the experiment. The then part is our predicted or expected results. Now, the idea that we have here is we want to be able to identify all these things. That's what our end result is. But the only way that that'll work is if they all have what? They all have to have something that we're testing here. What are we testing in this lab? Is a general term. It's 2 words and they both start with P. Physical properties. Okay. The idea here, guys, is that every material, element, compound, doesn't matter, has its own unique set of physical properties. Okay. That's at least how we understand matter. All right. I would say the if part should probably talk about that. Okay. That idea. Because if that's true, and we test all of their physical properties, then we should be able to do something at the end. Did y'all catch that? Because I pretty much laid it out there again. Okay. If, and then. So in the if part, okay, we should talk about unique physical properties. Okay. The and part briefly describes the experiment. So I would say like a brief description would be maybe tell me what physical properties we're going to look for. Okay, so the physical test will be run to determine the following physical properties: color, solubility, whatever, of each substance. You don't have to go into detail, just say in general, these are the things we're looking for. Okay, and then the then part is what we expect to find or be able to do at the end of the experiment. We're hoping that we're going to be able to what at the end of this experiment? Right, be able to identify the substances because they have different physical properties. Okay, so the then part needs to talk about how our results will allow us to do that. Okay. Okay, so I mean, you're going to put that in your own words. Everyone's going to have a slightly different spin on it. Incidentally, on that note, everyone's going to have a slightly different spin on this. You are going to be working with a group, okay? And I understand that when you work with a group, some things are going to be similar, right? Like, for example, you guys are going to write up the procedure for this lab with your group. So I expect that your procedures will be pretty much the same with your group mates. I'm okay with that because you're coming up with it together. However, this first part of the lab, that should be unique to you. Okay, your problem should be worded slightly differently than your group mates. Your variables, while the same, should be worded differently, okay, because you did it as opposed to, well, I told so-and-so to do this part of the lab, I'm doing this part of the lab, and Joe Blow is doing this part of the lab. Okay, that's not how that's going to work, okay, because they do not want to see 4 identical labs handed in, okay, from 4 different people. I'll notice, okay, and I won't be impressed. Okay, each lab needs to be unique. And I understand there's going to be similarities. Like we said, the procedure, that can be identical. You're coming up with that together, right? Your results, hopefully, are going to be the same as your group mates, because if you and your group mates get different results, there's a problem, okay? And things like that. That I expect to be the same, right? But other stuff, conclusions, and these kind of things, those need to be independently done, all right? Everybody follow me there? Okay. Now, for your materials, okay, within the materials are the unknown samples that we're trying to identify. One of them is ammonium nitrate. Okay, and we talked about ammonium nitrate a little bit on Friday. It's the stuff that's in the commercial cold packs, the ones where you pop the little blister, okay, that's full of water and you shake it up and they get cold, okay? So that's one of them, okay? We got copper 2 sulfate is another one of the unknown compounds. Now, what you're going to need to do after tomorrow, when you have all of your data, is look at these unknowns and start thinking up what would their properties be, and see if you can match those with some of the results you have. Okay, so as an example, right, ammonium nitrate, we just said, when it combines with water, it gets colder. So that's something I would probably find in the solubility test on one of my unknown samples. One of my unknown samples is going to get colder when I run the solubility test. Okay. Now, ammonium nitrate, is that an ionic or molecular compound? It's ionic. Yeah, it's ionic. Right. Ammonium is an ion, and nitrate is an ion. Okay. This is an ionic compound. Right, which means that it should dissolve pretty easily, and its solution should do what with electricity? It should conduct electricity, right? That's the thought process that you need to go through for each one of those things. And if you want to Google it, that's fine. Okay, I don't have any problem with you going online and going physical properties cobalt-2 chloride. Okay, and looking. I just would not necessarily trust all the pictures you might see if pictures pop up. Okay, but you could look up things like that, and that might help you. Really, you should be able to do it with just the notes that I've given you. But if you want a little extra help, there's nothing wrong with doing that either. Okay. All right, another unknown, ethanol. Okay, ethanol is alcohol. Okay, it's a type of alcohol. There's lots of different kinds of alcohol. By the way, don't drink that. We already said don't drink anything in the lab, but definitely don't drink this. It's denatured. That means you don't get drunk. It means you get blind. Yeah. Okay. Don't drink it. Okay. And then paraffin. What's a more common name for paraffin? Where do you see it usually? It's in candles. It's candle wax. Paraffin is candle wax. Okay, so looking at the formulas for these two here, they both start with non-metals, which means they're probably what? Molecular. Okay, they're going to have different properties. Okay, sodium chloride, which is common table salt, is one of our unknowns. Sodium hydroxide, we talked about that as well. That's the stuff that's in oven cleaner, and we said it was a really strong what? Base, right? It's got OH in it, and we talked about how anything that ends in OH and is an ionic compound is likely to be a strong base. This is an ionic compound, right? Hydrogen chloride, similar, okay? Ionic compound, hydrogen's acting as the metal, which means this is going to be a very strong acid, okay? Things like that, all right? Sucrose, which is just regular sugar, okay? Water is one of our unknowns, cobalt-2 chloride, nickel-2 chloride, okay? These are all of our unknowns. We're going to be identifying those. Okay, questions on that? Okay, the other materials listed there. Okay, you got scupula, which is just a little lab spoon or scoop. Okay, there is a lab scoop in each unknown. It must stay with that unknown, unless of course it's a liquid, in which case there'll be an eyedropper instead. Okay, but why don't we want you to take the scupula from A and use it in B? Right, then the samples are contaminated, right? And worse than that, they could be reactive with each other. And I don't want an uncontrolled reaction happening in the samples, all right? So we don't want to be mixing any of the samples together. If you forget which one you took it from, just bring it to me and say, Mr. Coderre, I forget which one I took this from. And I'm going to go, that's fine. And I'll wash it off and I'll figure out where it goes. Or I'll grab another one and put it in one that doesn't have one or whatever. Okay. But the worst thing you can do is go, this one? No. Okay. We do not want to do that. Okay. Because we'll contaminate the samples and then everybody's data is going to be messed up. And what's worse is no one will know. These are all unknown samples, and if we mess them up or contaminate them, people get the wrong results and they won't know until it's too late. Okay, so make sure that if you forget which one you took it from, okay, you come and tell me. Okay, so the other things here, the other materials. Obviously, I already showed you the depression plate. Okay, so a little ceramic dish with little depressions or divots or pits or whatever you want to call them in it. Okay, and you're going to be putting samples in there. How much sample are you going to be dealing with? Yeah, just a small amount. All right, now we did say one of our controlled variables was the amount of sample that goes in each one of these. We're not going to be taking the mass of each material. It takes forever if we actually measure out the exact same mass of material for each one, right? So what's another way we could kind of make sure we have about the same amount? Yeah, eyeball it. Yeah, I know doesn't sound terribly scientific, but eyeball it. Okay, I would say that you should probably fill each depression to about 1/4, maybe 1/3 of the way up with unknown sample. Okay, because if you pile it in there, then when you start doing the solubility test, it's going to spill into the other depressions and contaminate them, and then you're going to be in trouble. All right, so everyone follow there? Okay, we should probably write that down in the procedure. Okay, because when you write out your procedure, that's one of the things you're going to want to write in there is we're going to fill these about 1/4 of the way full with sample. Okay, I'm sure you've all seen one of these before. Hopefully you have. This is a thermometer. Some people call it a thermometer. It's actually a thermometer. Okay, when do we want to use this? What test is this going to be part of? It's part of the solubility test. Okay, now we know kind of the starting temperature of everything. So when do I want to put it in? Like I've got my unknown sample. Do I want to add the water and then put the thermometer in, or do I want to have the thermometer in and add water then? Okay, let me say that again. What order do you think that I want to do this in? Add water to the sample and then put the thermometer in, or have the thermometer in and then add water? Have the thermometer in and then add water. You are not dealing with very much sample here. Any temperature changes that occur are going to be very quick and likely small. All right, because you're dealing with just small amounts of everything. So it's best to have the thermometer in there when you add the water. There's another reason it's good to have it in there, because if you add too much water and then put this in, it'll displace some of the water and push it possibly into some of your other samples, and then you'll have to redo those ones. So it's best to have it in there and squirt some water in. How full should we fill it? Like, should I make it so that it's right at the very top? I wouldn't think so, no. Okay, I'd say with the thermometer in there, about 3/4 to maybe 7/8 of the way full. Okay, that way, when you take this out and run the next test, you don't have to worry about pushing water out and into neighboring depressions. Okay, everybody following on that? Now, when you're looking at the thermometer tomorrow, don't expect to see like 10-degree jumps. Okay, if you're straining and going, oh, is it like 1/2 degree change or whatever? It didn't change. Okay, you could change it 1/2 degree just by holding it with your fingers, right? Incidentally, they usually have a little red piece of plastic on them, and you hold the red piece of plastic so that your fingers don't actually touch the thermometer and interfere with the reading. Okay, they should have a little piece of red plastic on them. This one doesn't. Okay, all right, so these are delicate, obviously. Okay, so I shouldn't see anybody going, oh, I'm just gonna mash this sample down because it doesn't seem like it's dissolving. Okay, this is not a stirring apparatus. Okay, so please don't treat it as such. Okay, I mean, if you want to give kind of like a gentle yeah, that's fine. Okay, but don't be trying to crush crystals with this because you'll break it, right? And well, then we have to replace it. So try not to do that. If you really desperately want to try and break up some of the crystals, I can get you a stirring rod and you can use it for that. But for the most part, you're going to know whether they're dissolving or not. It's pretty obvious. Okay. All right. So once we're done the solubility test, the next test is the conductivity test. Okay. So this is your conductivity apparatus, exactly as I described the other day. It's got 2 leads, 9-volt battery on the top, and there's a button on the side. Okay, when you press that, so you put it in the solution and then press the button. When you press the button, the little red on light will come on. Okay, that way if it's completely non-conductive, and there's a couple that might be, okay, and none of these light up, you'll know it's actually working. All right, if that little red light doesn't come on, then come tell me and I'll get you a new battery. Right, but I'm pretty sure they all work. I tested most of them. Okay, so you put it in there, push the button, and just read the number off the face. It's probably the easiest test we have. Okay, questions on that one? All right. And then the last test is your pH test. So pH paper will come in one of 2 containers. It'll either come in a tube or a vial like this, or it'll come in these kind of transparent yellowish orange containers. Okay, either way, each one of them has hydrion paper inside or pH paper inside. Okay, the vials have these kind of longer pieces. I would say that one of those pieces can easily test 2 unknown samples. Okay, so rip it in half and do 2 tests with it. Okay, and then once you dip it in, the change is immediate. Okay, you don't need to hold it in there. Just dip it in and right away it changes, and then you just match it up with the color on the guide. Okay, if you're using the ones that are out of the yellowish orange transparent package, right, then take this out. It looks a lot different in the yellow than it does out of the yellow, okay, and you want to get a true idea of the color. Okay, again, same thing here, just rip off a piece that's, you know, maybe 1.5 centimeters long or so, okay, and use that to test. We don't need a, you know, piece this long to test a tiny little bit of sample. Okay, all right. So you and your group today are going to work on the top part here together, and then you're going to write up the procedure. That is the steps that we're going to follow. All right. So we said we're going to run the tests in the following order. The first, well, actually, when you write this procedure, you have to write it assuming it is for the dumbest person you've ever met. Don't name names. Okay. But you have to assume that the person following the instructions does not have any idea what they're doing. You've got to lay it all out. So your first step in your procedure should be put on safety goggles. And like, I mean, it's got to be, you got to lay it right out for them. Okay. Second step, go to front table and acquire samples. Okay. Fill each depression 1/4 of the way full. You have to be that specific. Don't just say, go get stuff. Right? I'm not going to be terribly impressed if I'm reading your procedure and the first step is go get stuff. What stuff? I don't have no idea. Okay, be specific. Okay, what test did we say we were going to run first? Nope, before solubility. Before we run the solubility test, we have to run the observable properties test. Okay, so that includes things like color, odor, state, nature of matter. So if it's a solid, is it crystalline or soft? Is it, if it's a liquid, is it viscous or thin? Okay, is it clear or cloudy? Right, all of that kind of stuff. Those are all the kinds of things that need to be mentioned. So when you're saying run observable properties test, you need to say look for the following and record in chart. Okay, for solids, do this. For liquids, look for this. Okay, and so on. Make sure you tell them exactly what to look for and what to record. A good procedure always does that. Okay. Once you've done the observable properties test, then we want to do the solubility test. Now you'll have a little wash bottle. Okay, it's just a little like plastic water bottle that you can squeeze, and it's got kind of a little spray nozzle at the top. So you squeeze it and water will come out. Okay, be careful. Don't squeeze it hard because it'll create enough pressure that it'll shoot your sample right out of the depression. Okay, you want to squeeze it just enough to get some drops in there. Okay, and get the test going. Right. During the solubility test, again, you want to tell people what to look for. Okay, look for temperature changes. Temperature changes indicate the material is dissolving. Look for change in the shape or size of crystals and stuff like that. Tell them exactly what to look for and what to record. Okay. Then you got the conductivity test, which is pretty easy. Put the conductivity test around and push the button and write the number down. Okay, say it a little more scientifically than that, but okay. And then lastly is the pH test. Tell them how much pH paper to take, dip it in, compare it to the chart, etc. Okay. Now, you're doing those same batteries of tests 12 times. Do you need to copy and paste it 12 times? Please don't. I had a group do that once. Their lab report was 15 pages long, okay? Because they had the steps. It was like, I don't know if you've seen The Shining, but it was like the book that he wrote. It was like all work and no play make Jack a dull boy. And that was the whole thing, okay? It was the same steps over and over. It was really creepy to read, okay? So you can just write down the steps once, and then for the next step, say, repeat steps 2 through whatever for each sample. Something like that, okay? Just so that you're saving yourself and me a lot of time, okay? Okay, so when you're done that, then basically you're ready for tomorrow, all right? So for tomorrow, what I expect to see, Okay, so tomorrow what I expect to see is that you've got this stuff kind of filled in, although I'm less worried about the first bits here, okay? But that you've got a procedure ready and you've got this chart ready, okay? Because you need this chart to record your observations in. So what I would suggest you do for tomorrow is either make a hand copy of this, like hand-drawn copy with more space, okay? I mean, this is just kind of the minimum amount of space, but you'll probably want more space for it. Or tonight at home, like, put the cursor in here, press return, and make them all bigger and print it off. Okay, one way or another, you need a paper copy of it tomorrow so that you can record stuff in it. We're not taking the Chromebooks across the hall to the lab. Okay. All right, everybody follow what the expectations for today are. Okay, you need to come up with a procedure with your group mates. Now, another thing, question that came up in period 1 today was, should my procedure be a paragraph or a numbered list? What do you think? It should definitely be a numbered list, okay? And nothing is worse than trying to follow instructions that are in paragraph form, because you read the instructions and then you look away to do something. Now you pretty much have to read the paragraph over again to find out where you were, right? If you have a numbered list, you can remember you were on step 2, okay, step 3. So a procedure should always be a numbered list. So make sure that yours is a numbered list. All right, and like we said, be thorough, be descriptive. Okay, if you do a good job of this, you should basically be just finishing writing up the procedure by the time the bell goes at the end of class today. All right, and then tomorrow we go across and we actually perform the procedure and get our results. When we have our results, so this chart is all filled in, okay, then you'll be able to do the analysis part. There's only one thing to do in the analysis, and that is decide what is A. Okay, is A ionic or molecular? And what, in fact, was it? Was it ammonium chloride? Was it water? Okay, was it sugar? What was it? Right? That's all the analysis is. Okay, then you'll have your conclusion after that, where you'll copy and paste your hypothesis, and then say, based on our observations and our analysis, we can accept or reject the hypothesis for this reason. And then in your evaluation, 2 sources of error and how to fix them. Remember, we want design errors, not performance errors. Okay, we talked about that on Friday as well. If you weren't here on Friday, make sure you watch that podcast about how to make a proper lab report. All right, groups of 4, please. Okay, we need to have groups of 4. Now listen, guys, if you don't end up in a group, just let me know. I'll put you in a group. Okay, but let's try and include everybody, okay, so that everyone feels welcome and included here. Okay, probably best to just pick people around you. Okay, that'll probably work best for everybody. All right, so make sure you got a group of 4, no bigger. I don't want too many smaller either. That's just kind of the way the lab is laid out. So make sure you got groups of about that size. Okay? Let's stay focused and on task, guys, and get this done. Okay, off you go.